So we'll get started with the webinar. My name is Bernie Zuzo, and I'm very pleased to be the moderator for TRDA's first in a series of webinars. If you had struggled during college, graduate, undergraduate, and postgraduate looking for the right room you're in, let me tell you that this virtual room is the webinar for understanding the technical development cycle. And I and my colleagues, Don and Rita, want to welcome you to this webinar. We've defined what the technical development cycle is. During this webinar, we would like to explain that the technical development cycle is actually a progression of technology from the very early stages in research all the way through a number of major phases and steps to the end-use product. The development cycle actually has several phases. We'll talk with you about each of the three phases in the technical development cycle, and within those phases there are some steps that we'd like to tell you about so that you can walk through these phases and get to the next one. And those steps include a number of terms which you'll hear us repeat several times during the day. TRDA, the Florida's Technological Research and Development Authority, is the host for this series of webinars. We're hosting these webinars because of a special program that we have received funds from the state to develop and implement, the Clean Technology Ventures program, and the webinar series is part of that program. TRDA is a special district for the state of Florida. It was created out of the legislature back in 1987. For more information about TRDA, its mission, its programs, please click on the website, which I have on this particular slide. Presenters: Don Platt, who is the president of Micro Aerospace Solutions, and Rita Ward, who is the CEO and founder of NOAA Industries here in Melbourne. They're going to introduce themselves personally in just a minute. I'm Bernie Zuzo, and I work for Florida's Technological Research and Development Authority as the manager for SBIR commercialization.
My name is Don Platt, and I'd also like to welcome you to this webinar today. It's my pleasure to be here to talk to you a little bit about the technology development cycle. As Bernie said, I am president of Micro Aerospace Solutions based here in Melbourne, Florida. We're a small engineering services company that provides design and product development support for a number of businesses in a variety of different disciplines, including aerospace, embedded systems, and communications. I've been involved with a number of projects through the years, trying to tally it up to probably over 50 projects. The typical clientele that we deal with are entrepreneurs, organizations, universities, and nonprofits. One of the things that I really enjoy about the whole entrepreneurial process is developing things that have never been done before. And I'd really like to hear from you guys, and so you can send me an email or call me at the contact information on the bottom of the screen.
Thank you, Don. Rita, would you be kind enough to introduce yourself?
Yeah, good morning. My name's Rita Ward, and I'm the founder of NOAA Industries, and we are a design as well as a prototyping company. And what we do is we focus on taking technology and implement it in product design and prototyping and getting the product into customers' hands or the end users' hands for industrial and government markets. We specialize in having all disciplines underneath our roof. So if someone comes to our front door, we can help them design it and get it to a product. The number of projects we have completed, it says 50 on the sheet there, but it's over 250. And the typical clients are entrepreneurs and startups we've been in business about 12 and a half years, and the biggest thing that we enjoy doing is supporting the new ideas that make lives better. Because over time we see that there's an end user that his job becomes more efficient, or a client that is able to produce something and have his own company. Feel free to email me or call me at any time.
Thank you, Reader. As I said before, I'm Bernie Zuzo, and I work for TRDA in technology commercialization. I've been involved in technology commercialization for over 25 years in the three sectors of industry, government, and education. I'm sorry about the error, Reader. I've done and completed over 200 projects, both technology and business. And like Don, I work, like I mentioned, in a variety of segments. My contact information is here also, and you're welcome to contact me in the future if you like. The objective of this webinar, we'd like for all of the attendees to improve or gain an understanding that development is actually a continuum. It's a continuous process from the concepts that come out of research and some just plain inspired people to the finished products that eventually will be distributed and sold. You as attendees, we would like to present the information in a way that you end up having the knowledge to either improve or initiate your own technology development roadmap, advancing your technology into designed products and into products that fit into a manufacturing design process and eventually into the hands of final consumers. So we want to provide some understanding, but we'd also like to give you some tools that you walk away with. In terms of scope of this webinar, I will tell you what we will talk about and what we will not talk about. The focus of this first webinar is to take a look at the technical development phase. That technical development phase is going to come to this point right here. We'll look at the technology development, we'll take a look at product design, we'll take a look at manufacturing design, and by the time we're done with these three phases within the technical development cycle, we will have hopefully provided tools so that you can show that you can in fact design the concept and the ideas that you have. What we will not talk about is from this point forward in the this is the product development cycle. We will not talk about the marketing and the sales to get into the marketplace initially, to expand that penetration, to deal with growing the company from a business perspective. Eventually the product gets mature and starts to decline, and so we're not going to talk about those phases in product life cycle. We're going to focus on the very beginning phase, which is the technical development cycle. There's a special thanks to Dr. Edward Large down at Florida Atlantic University, who's the founder of Circular Logic, one of the companies which was screened into the 2009 Commercialization Assistance Program. The technology which Ed has is a technology he kindly gave us permission to use as illustration of the various principles that we'll convey to you today. The Commercialization Assistance Program here at TRDA is in its fourth year. It's been funded by both NASA and DoD to provide commercialization assistance to their small business innovative research grantees. Those grantees have received up to $1 million, usually around $750,000, in order to develop new technologies. Ed has been and still is one of those recipients. Thank you, Ed. Don, I'd like to turn this over to you and let you get started on the very first phase, the technology development phase.
Thank you, Bernie. As Bernie just said, the technology development is sort of the foundation, initial phase of the development of a product, and on through to being able to have something that you can market and sell. So in terms of the big picture then, we need to identify the types of technology that your company may have. The technology could be something that is enabling. It enables a series of products to be developed. It could be a breakthrough technology, something that has never really been developed at all before, and you're sort of really pushing the cutting edge. It could be incremental technology that's just building on things that you've already created, or it could be a core series of technologies that you can then spin off a number of products from. Much as you do in the SBIR process itself, you need to think about the novelty of your invention, of your technology, what you have that is different than other people, what you have that you can say is different than any of the competition. And so what we need to do as part of the technology development cycle then is to translate this basic technology into engineering terms. What do you need in the engineering world to move this technology from a concept on through to a real product? Much as you have to think about what do you need from the business point of view to do the same thing. And so this process here then puts legs into your technology and gives it the ability to move forward.
Don, would you be kind enough to tell us which type of technology Dr. Ed Large's technology at Circular Logic is?
The Circular Logic technology was very unique and different, so it was actually a breakthrough technology that was never, its particular aspects were never really seen in the signal processing world previously.
Thank you, Don.
So there are a series of steps required then for the technology development. First off, we need to identify the problem that the technology solves. There may be a variety of different kinds of users that could benefit from this technology. And so for those users, how does your technology solve some sort of an issue that they have? And then you really need to be creative with the next step and think across as many disciplines as possible for identifying new product applications. Bernie and I sat down with Circular Logic and identified several dozen product application areas. So you really want to think outside the box during that phase and not limit yourself. And then you have to think about the technology function and features. What about the technology, what particular aspects of the technology need to be developed? What are the functions and the various little sections of the technology that have to be integrated together to produce a product? Think about the competition. How have they done a similar integration process? What kinds of areas have they been working in to progress products previously that may be a little bit similar to what you have? And how is the technology that you have then different? How does it improve products? How does it make a product totally different than what they have already? And you need to then build all of this into a proof of concept, starting with calculations and a feasibility study that then actually at the end of the technology development cycle will result in a breadboard type of device that you can then take initial measurements from for benchmarking. We then need to translate all of this into an engineering capabilities. What do you have available in-house? What don't you have? And maybe then you need to have partnerships with other organizations, ways to then translate and transition this technology forward. So, in terms of the example of Circular Logic's technology, the basic problem that this technology was solving is that, for the most part, we are currently dealing with audio technologies that employ linear signal processing algorithms. The problem with this is that it only very narrowly approximates the human auditory perception capability. And then to mimic the actual human capabilities for audio processing of sounds, then a nonlinear algorithm was developed by Circular Logic, and then the processing capabilities for that algorithm are implemented. And that is really what is required then to move the technology forward, to make it really a breakthrough technology, to move beyond what previously has been really just a linear realm.
Don, I want to highlight this word linear because it's critical in Ed's technology, isn't it?
Yes, and his ability to move beyond that linear step, absolutely. So as I said, Bernie and I sat down and we just sort of brainstormed on various product applications for Circular Logic's technology. Clearly, of course, music would be a fundamental one. You have maybe someone that's playing a piano and they come up with a piece, but they really need to document it. So using this nonlinear sound processing algorithm, you can have a device, a product, that can then read the music as it's coming through the piano and translate it into a musical score. You could take old music and put it into a musical score. Then maybe it's a very old record or something, or a tape from many years ago. The security industry has an important application here for identifying various unique sounds that are in the environment. Perhaps you have a series of microphones set up around a building, a home, maybe for instance in the evening, and it picks up some unusual sounds. It has a database of different types of sounds. The sound of a person walking has a unique aspect to it. So therefore, your Circular Logic device could then trigger a video camera system to record only during interesting times. Clearly, this would be then an advantage that you don't have to sift through hours and hours of video to see something that is interesting. There are many other applications here that we've defined, and this is really just a small number of all of the ones that we were able to put together for this technology. So what we need to do then is look at the physical elements of what the technology is dealing with or interfacing with and match it up with components then that have to be developed. And so that's what this map here is showing. So for instance, when we're dealing with sound, we have to then have some sort of a way to record the sound, to capture the sound from maybe a voice or a piano or some sort of a vehicle. We need to then have a model of a human sound or auditory processing system. So it has a number of levels. So in a way, you could think of it as sort of simulating the nerve signals that are responding to various sounds in the environment. And so that's what this device is doing, and so they have developed a model to do that. The amplifier and sensor are equivalent then to the outer ear of the human, receiving the sound, bringing it in, amplifying it, and sensing it. And then we have pattern recognition that then identifies through a library the sounds that are being created and matches them up with a library that's already in the device itself. This is then similar to the way that the cilia inside of the ear vibrates, generating nerves signals that are different for each different kind of sound that you may be receiving in your brain. And so the signal processing then is sort of mimicking that along with the actual cilia movement itself to create the signal. Now the FPGA, or field programmable gate array, then is sort of the integrated circuit implementation of the algorithm itself and the routine to match up the sounds with a series of library stored database pieces of information so they can then identify the original source of the sound.
That's quite a mapping.
It's quite a mapping, and this is something that you really need to spend a lot of time on, because this allows you then to identify what you really have and what areas you need to develop and concentrate on. When you do this kind of a mapping, then you can see clearly where you are progressing, where maybe you're lagging behind and need to spend more effort, more resources, maybe be involved with other groups to progress some of those technological components forward.
Don, when we first talked with Reeder and Michael Stouffer on his team, we heard explanations that sounded like the technology was the physiology of the ear and the brain and the nervous system between. We also heard explanations that it sounded like it was signal processing. We also heard explanations that sounded like it was sophisticated math being adapted in this area and very specialized algorithms. How did we sort through that? What did we do that finally Ed knew and Michael knew what technology they had, and we at the same time came to know what technology they had?
Yeah, well, you really have to sit down and you brainstorm, you put it onto a piece of paper or whiteboard, you identify the key components of the technology, what is it doing? And through this iterative process then, looking at all of the documentation they've developed so far, maybe some patents have been created, identifying what it is that's unique and what it is then that this technology is and what it is not, because that's just as important in order to be able to move forward.
At some point, this is Bernie speaking, at some point I'd like for both of you to identify concurrent technology that is needed so that we can underscore the importance of seeing the whole landscape around a technology. Technology fits into part of the landscape, but you can't get the whole picture unless you have the concurrent technologies developed as well. Ed has some concurrent technologies that need to be developed in what really is a very demanding long-term plan for his technology, doesn't he?
Yeah, this is Don. He one of the really concurrent technology areas that he had to develop a capability within is the idea of the FPGA itself, because he had this algorithm,
field programmable gate array, which is defined as?
It is basically an integrated circuit system that allows you then to program a sophisticated algorithm into a computer device so that you can then create an electrical circuit within inside of this FPGA that does the very unique nonlinear aspects of the design.
Okay. And he has to map the cilia, doesn't he? As the cilia make movements to send out signals to the brain, each combination of cilia and movement represents a specific sound.
Yes.
That mapping hasn't been done yet it's a very critical part of the development process, isn't it?
That's all part of this idea of developing a library.
So concurrent technologies are crucial to recognize if they're needed. Otherwise, you find yourself getting a big surprise as you make a big investment.
And you don't want that.
And the proof of concept doesn't prove.
That's right.
Reeder.
This is Reeder, and what I wanted to add was you come to a slide like this and you think, wow, this is overwhelming. I mean, that's what I think when I look at it. And I've been through, over the 20 years, over 250 product developments. And we all need help. That's what really strikes me about this, because even when we develop the technology, we get to the point to where we might be able to get the number 1 or 2 or 3 on this slide and get them mapped, but we need help from the outside to look at the picture for us, because a technologist is a very special person, but he's very focused on advancing one technology to that next level.
Reeder, this is Bernie speaking, Reeder, when you look outside the technical group who brings the technology to you and you begin the mapping, and there needs to be some other eyes, are those other eyes different engineering disciplines, or are they different scientific disciplines? Who are these other eyes?
What we tend to use is engineering disciplines and the guy off the street, and we try to compare those two answers with one another. Are they giving us the same answer? And when I say guy off the street, that's often my function, but we have several consultants that work with us that will bring in and just say, what do you think about this technology? And if things start to line up from the advantages standpoint, then we know, hey, there's something good here.
So these people, this is Bernie speaking, you bring people in who aren't biased, who have an open mind, and who have a different perspective on the way they look at this technology that's been brought to you.
Right, no skin in the game. That's what we try to have.
So then, once we've identified the technology and the physical aspects and their correlation or their interface, then we need to identify the components themselves. And so what this diagram here is doing is showing all of the components of the technology and how they interface with one another. So this allows us first off to clearly know what components need to be developed and tested, but we also at this stage can then see how they're interacting with each other. So for instance, with the circular logic example, we have the sensor that is picking up the outside world. So that's sort of the direct interface with the outside world of signals. Those could be sound signals, RF, which is radio frequency, so some sort of radio transmission that's being coming in. Because as we looked at the technology here, we understood that the same types of signal processing capabilities that are used to identify sounds could also be used to identify other types of sources of information, like radio signals, for instance. And they're very similar, and so the same kinds of processing techniques could be used for either realm.
This is Bernie. Don, when we spoke with Ed and Mike and his crew, did these other signals, the radio frequency signals, in addition to the sounds they were looking at, such as music and voice, did they recognize these other kinds of signals as being pertinent to the kinds of signal processing and linear, nonlinear math conditions they were looking at?
Well, I think one of the problems that a technologist often has is that he is so buried in focusing on developing the technology for the realm that he has maybe some experience in or some exposure to previously, that he may not really be able to think enough outside the box to recognize that there were these other opportunities out there. And so that's not really a failing of anyone. That is just the way we as humans operate. We're really focusing on developing it here. So oftentimes we need somebody who's a little bit back from the process to help out and identify all of these other areas where the technology could be implemented.
So, like Reader said, in the engineering design phase, he brings in other people who have different perspectives and see with different eyes. In the earlier stage, in the technology development stage, the same thing can be done.
Absolutely. As we said, we need to be creative in that stage. We need to really look at all those potential opportunities and not close doors on anything. So as we move forward here, then we need to amplify those signals and get them into an A to D converter, which is an analog to digital converter, which takes the signals from the outside world and translates them into a digital set of ones and zeros. The reason why we need to do that is that the algorithm is running in a digital computer environment, this FPGA that we just talked about. And so we need to translate it from an analog into a digital world here so that the algorithm can deal with those ones and zeros then. The algorithm then is working through this simulation model of the various types of responses to sounds, and it's matching up then the response that it sees with a database.
Don, would you be kind enough to define the algorithm?
Well, the algorithm is really sort of a solution to how to process these signals, a way, a technique.
Is it an equation, a math?
It's a series of equations. It's a whole routine, if you will. And so then the FPGA is where all of these sort of really interesting and unique aspects get implemented here, and then into an end-use device. Now, this end-use device could have different forms and factors depending on whether it's going into a security system, if it's going into voice transcription. Say, for instance, you have somebody in a courtroom that wants to translate then what is being spoken into a documented record. It could be a different type of environment. for all these end-use applications. And so that's really where the product development sort of fits in there.
I'm speaking on behalf of Ed here. This is Bernie. Ed loves music, and the driver for him was to be able to develop a technology that was so accurate when it heard a sound that it could be translated through science and engineering into a format that would communicate with a printer or computer and a printer,
Right.
and the precise note that was heard would actually be put on the music sheet. And so for Ed, right here, Ed, this is for you. Okay, Don, back to you.
Yeah, so what we really need to do then is to identify this differentiating feature. So again, using the circular logic example, the differentiating feature, as we said, the key aspect here is this idea of a nonlinear processing system. Now, a key feature of something that's nonlinear then is that it is very flexible. And so in order to be able to identify all of these different sounds and match them up with what actually created them, we need to have this ability to do something that is nonlinear.
And non-linear as opposed to linear means that it happens randomly,
Yes, over a
non-sequentially.
variety of different frequencies, if you will. And so it could be, in a way, a little bit unpredictable. A linear system has to have things in just sort of a real lockstep way in order for it to work properly.
Did you get to this?
The nonlinear capability then correlates the responses of the cilia of the inner ear to the nerve signals that the brain then receives for each sound. And so that's really what's happening with the circular logic technology.
It's so important, this is Bernie speaking, it's so important to know how the technology is differentiated, because there are cutting edge technologies that are in the early stages.
Yes.
It's very hard for a third party or an investor to know which horse is going to win the race.
Yes, definitely.
So as researchers do literature searches to define what the state of the art is and how their particular research proposal will be different, it's very important to understand how one's technology is particularly different from other technology horses that are in the early race. So differentiating it is critically important.
And this is a fundamental step for the technologist to do, because he has to be able to understand how his technology is differentiating, or no one else is going to give him credit for what he has. So it's crucial.
Plus he needs to have differentiating feature in order to prepare his intellectual property
Absolutely.
description in order to differentiate himself in the end-use product in the marketplace.
All of that area, all the way from identifying the IP on into getting investors.
Okay, this is Bernie. I'm going to jump in here. This is a matrix we love. We would like to have one webinar only on this matrix here. The matrix that we've developed is a matrix which takes our three phases in the technical development cycle: the technology development phase, the product design phase, and the manufacturing design phase. And there are certain activities that are the same in each of these phases. You need to do them, but the way you do them is different. We've never seen clarity before across this full cycle. So we wanted to develop it for this webinar. And what we will present to you now is each of these activities across the three different phases. So Don and Reader, I'm going to ask you folks. Don, you take the technology development cycle first, and Reader, you take the product design and the manufacturing design phases, and explain how proof of concept needs to be done in each of these three phases, but what is done in proof of concept in each of these phases.
Certainly. This is Don. From the technology development, which, as I said, is sort of the foundational phase, it's the very beginning of all of these cycles here. What we need to start out with is the mathematical background, calculations, simulations perhaps, to identify the feasibility of the technology and how it could then solve some sort of a problem for different types of users. So here we're looking at, this is really something you've probably maybe done already as part of your SBIR project, if you're working from the SBIR realm, where you're identifying the feasibility of the technology. Can it really solve the problem at hand? And so at this phase, for the proof of concept, we are just sort of doing, for the most part, again, for identifying proof of concept, a paper study, a computational study to determine if it's possible.
And so this is Reader, and we get these calculations which the technologists give us, and we try to determine what can we build from it. What kind of things do we need to put together to verify its physical performance? And we try to do this in a way to where we take the paper study and we implement drawings from it. We choose parts and we try to define everything really down to the last little nut. And then from there we go into the manufacturing design, where we take that design, the physical performance of each of the components, and we do a pilot project where we will build 30 of them and test them. Which brings us to the development tools.
And this is done from the technology development part of the cycle. The development tools used include simulation tools, simulation capabilities. Maybe it's a fluid flow simulation. Maybe it's an electrical circuit simulation. And you may have to have research labs involved that have these special capabilities at this phase. And then we are moving into then the realm of developing actual hardware, and so at that point you're moving into the rapid prototyping phase, quickly developing a simple prototype.
Don, would you give an example of what rapid prototyping is as opposed to more ambitious prototyping, such as we talked about vacuum forming versus a plastic mold?
Right. When you get into the, and Rita will talk about those areas more, but as you get into the product itself, you're getting into something that can be manufactured on a large scale. Here with rapid prototyping, you're just interested in a few, maybe one or two devices, and so it could be something like a 3D printer that just receives a computer file and can build up a model that actually might be workable, and at least you can see then the form, fit, and function of the device itself, but it is not something you can manufacture into a product.
Thank you.
And we often, this is Reader speaking again, we often take that rapid prototyping model that Don has developed in his shop, and we try to use that in our first level of test. We try to implement as much as the technologist has developed so that we're not going over the same territory. And we encourage technologists to do that rapid prototyping step in the technology development because it answers a lot of questions for them. The problem-solving expertise, I'm going to focus on two things here. The problem-solving expertise is important from the different disciplines standpoint, because we're taking something that's got to the point to where it needs to go through a product development cycle, and we try to solve the problems quickly, so each person must have an expertise in their area. The other one I wanted to focus on was the test to failure. Yes, I have a product, I have a proof of concept, I might even have a first order prototype, but you have to test it to failure. 25% above its rated load in many cases, and if it's mechanical, 50%. And so we take those products, or what I'd call prototype at that point, and make sure that it will work above its rated value. And then we take all that information into the manufacturing design, where we do a supply chain analysis, a critical part analysis, and also pilot runs. And the reason we're putting that on the chart today is the focus of any manufacturing design, we believe, is the best part is no part. Because if you don't have to track it, you don't have to buy it, you don't have to put it down, then that saves time and money and will help you in the end build a good business.
Should we move on to the manifestation of the prior work that you've been talking about?
This is Don, working from the technology development phase. I really want to make it clear here that at the end of the technology development phase, you actually do have a piece of hardware. You have to have a bench working model, and this working model demonstrates the overall feasibility of the technology. And it has to be fairly close then to what you will have in a real product. For instance, if you want to design a handheld device and your working model at the end of this phase has to fit on a very large table and use wall power, then that maybe really does not produce a working model that demonstrates the ability of the technology to be put into a product itself.
And so we take this bench working model, which we encourage all the technologists to do, because again, it answers a lot of questions for them as well as for us when we get into the product design phase. It shortens the product design cycle. So we take that and we design it so that we can make multiple prototypes. Then we test those, as I mentioned above, to failure. And then in the manufacturing design, we try to choose the processes and the equipment to make that product as efficiently as possible.
This is Bernie speaking. Reader, when you get into the manufacturing equipment that operates a certain way, if you're going to hold the equipment constant, do you ever have to go back and redesign the product?
Yes, there is a process that we go through. Once we make about 10 prototypes, then we look at the most effective use of the equipment to make the product itself, and we do a manufacturing redesign.
Okay, thank you.
To accomplish that.
Okay, this is Bernie. You guys have done a lot of work up to this point. Now there's some outcome from all this work. Don, in the technology development phase, what's the outcome?
The outcome at the end of the technology development phase should then be a report, which may be a paper report, but also a series of data measurements of the parameters that the model operated under, the size of the model itself, the amount of power that the model required to operate, the voltage drop in the model itself. All of this then can feed into the product design so that the product designer knows what kinds of parameters does he have to work under to create a working product.
And then we take that, and our output is drawings and specs. And I like to break it out into two things. We have a notebook with everything in it that we can hand to a customer, and they can hand to anybody to manufacture the product, with some questions, of course, later on, because the manufacturer doesn't know the complete operation. But also the specifications, that they can also hand that to the manufacturer if it's a high volume product, and they can determine, hey, did we build it to the specs on the testing end of it. And then the end part, which is, this is the great news, is you get a finished sellable unit. The key part being sellable there. If it was unfinished and you could still sell it, that would be even great news. So then it brings us to the validation of the 3 cycle phases.
And this is Don. From the technology development point of view here, you have to deal with benchmarking. And there are really 2 aspects of this. First off, you have to benchmark that the technology and the components of the technology have actually done the job. They've actually done, for instance, the nonlinear signal processing in the circular logic example. And then also the other set of benchmarking, as I said, was this ability then to measure the physical parameters, the operational parameters, and they have to be then documented so that you can move into the next design phase.
And then we take and we build alpha and beta. We do a lot of testing on the alpha and beta units, which takes us right into manufacturing design, and you think, oh, your job's just over with because you got betas units out. And then the real hard part starts. It's quality control. It's the most critical part of the manufacturing process, in our opinion. And you've heard the old Ford commercial, quality is job one. And that is so true on any product that we have developed. If we can develop and manufacture a quality product and it goes out the door, but it doesn't come back with any problems, you're way ahead of the game.
This is Bernie. Reader, in your validation product design phase, are your alpha tests tests that are done to evaluate the quality of the engineering, perhaps sensitivity analysis, or perhaps those failure analysis you talked about, and then go back and redesign and create a next generation prototype? And is the beta test the same kind of process, only with customers who use it and identify the problems that they're having, for you to then go back and redesign the engineering to satisfy the customer-oriented problems?
All the above. That's true. One of the additional features we add in both the alpha and beta test is, once we get to that point, we start trying to identify parts we can take out of the design. Because, for example, a real easy one is jumpers. You have jumpers all through your design as you're getting up to that. But it takes management courage to actually say, we don't need that jumper anymore. We don't need that zero ohm resistor. And once you get to that point, that's usually in the beta testing part of it, that if you reduce the number of parts, which feeds into the manufacturing design of quality control, your quality often goes way up as you reduce your parts.
Thank you, Rita. Next slide is, we are now going to step into the product design phase. Rita, would you kick it off for us, since that's your ballpark?
Yes, we have the key elements, the big picture. I enjoy looking at these, and what I'd like to do is just take a break for a minute and have everybody think about how many comedians there are in the world. Because I think the population, is somewhere around 5 billion or so, and I think there's 4.5 billion comedians. Well, there are about 4.7 billion inventors. And as they go through this process, and I'm an inventor myself, is we have to keep in focus the big picture. How funny is the joke? Meaning, how good is the invention? And each inventor needs to be able to look at themselves and say, yeah, this is something that I think I can sell. And then when it gets into product development, a lot of money is spent as you develop the product for end user. And so these 3 points on the slide: device purpose, what does it do? What advantage does it give people? Function, how does it do it? And the structure, how do you put it together to make it work? As the comedians try to do this with each joke, laboring over each joke to make it hit on the ear, so we have to, as we develop the product as well as the technology, because as I said before, a technologist is a special person because they do all the hard upfront work. Really, when it gets to product design, it's an easier job. It just takes more money because we're implementing something that's been invented. So we encourage everybody to take a step back before they spend the money in the big picture. In the specific product design steps, I wanted to just hit on a couple. The number one is the device purpose. We try to get everybody to focus on, now, what is this going to solve? What's its purpose? How does it make some user's job better, faster, easier? And from there, the system's features and its function. What are the minimum set of system features and function? Not the maximum, the minimum to get to a sellable product to the user. And of course, we have to go over the engineering disciplines required to design it. But again, I'm going to re-emphasize the design loading. Yes, this product works. It works one time, but does it work 100 times? And how many times does it need to work, and at what load? And then the system features and function. You know, what kind of system is it? What's its components? How does it interface to other systems? What configuration do you need to put the system in to make the user use it? Because if they want if they take it and they put it in their system, they say, hey, it works great in this configuration, can you add just one more app to it? Then they'll integrate it into their systems and they'll use it and become more efficient, and they'll come back for more later.
This is Bernie. You have noticed by now that we are not being totally linear here. You're seeing lists that are helpful guides, but we're not addressing each item in the list. We're intentionally doing that because we're constrained by time. We've tried to target this webinar for 1 hour, so we're touching on those items in the list that we think an explanation might be most helpful for.
And feel free to email or call us later if you have other questions.
Yes.
And this is another reminder for the webinar. You have text chat or text messaging in the lower right-hand corner of your screen. For the question and answer period, we'd like for you to write your questions there, and we'll screen them. But you can write questions at any time during the webinar. You don't need to wait until the very end. Rita, I'm going to turn it back to you and go to your next slide.
So, taking us back to the circular logic example, what we try to do is define the user requirement drivers up front. What's the source of the sound? The sensor, how sensitive does it need to be? Does it need to be isolated? The amplifier, what kind of gain is going to be required? And the A to D converter, what range? Is it going to be an 8-bit A to D? How fast does it have to be? What's the minimum signal that it needs to detect, which feeds back to the amplifier? And then we have all this software over here that we just see that as a block that means what kind of delay is acceptable through all these processing steps. And then all this feeds into the blue box up to the right, which is what application are you going to choose? And so we encourage people to choose their application early. You can change it later, but choose it so you have a target, which feeds on to the next step of actual implementation of these blocks into hardware. Which, as we're going into the hardware, there's certain design issues as budget. Yeah, we can get the hardware, but it's 10 times more expensive than a user would ever buy. So you have the constraints of the size and the weight, what kind of reliability, and the one that everybody tries to avoid is the regulatory requirements. If you don't have to go through that step, you don't want to. And then the technical skill of the user. There's the axiom of a user will get your product and use it incorrectly each time for the first 2 or 3 days, and then they'll call and they'll ask you what the problem is, and then you ask them, have you read the user's guide? And they'll say, what user's guide? And so the technical skill of the user also feeds back into your company of technical support.
It may also increase your loading sometimes, doesn't it?
Absolutely. A well-designed product makes and produced product makes it a lot easier on a small company. So now it's implementation. Source of the sounds. It's a piano. Oh, we know something. So something's been defined. So now we can go to the sensor microphone and we say, since it's a piano, we can't set it on the piano or we'll get feedback. So it's probably going to be isolated with the integrated amp. And then there'll probably be a post amp required because we're going to have to be able to have the sensitivity in the upfront amp, but amplification just to match the A to D converter. And we've chosen a 10 megabits per second A to D, excuse me, to capture all the different sound variations. There might be something really sharp, a real short note that you want to catch. And then this brings us back to the processing step. What's acceptable? Is it 0.1 seconds delay max? That's what we're saying is for music transcription. Now, that might not be in this particular application true, but in general, the processing steps for real time, you have to be less than a third of a second. and you try to have it as short as possible given your requirements.
And reader, is that, this is Bernie, is that because of the processing time of the brain? The brain cannot process a piece of information any faster than 0.3 of a second.
Well,
or whatever the parameter is.
Whatever the that's true. And we've, like one of the video applications we developed was they run at 4 frames a second. And that gives them enough information because the brain puts in the information in between them. But once you get to a 30th of a second, then you're really taxing the brain. It just sees what it sees.
I can just, this is Bernie, I can just see and feel Ed on the other end wanting to speak up on the physiology of this and wanting to talk about all these steps in here that we haven't talked about with regard to pattern recognition and all of his we just got a text message from Ed saying, yes, that's true. And Ed has, go ahead, reader.
And so this is really interesting. I love this kind of interaction because the technologist is saying, you have it all wrong. And as a product development, we actually say, yes, you're right. Now educate us so we can help get you to the next step.
Let me just add a little in this section in here, which we didn't talk much about, because Ed has worked very, very hard with a third-party collaborator, and I want to emphasize how, in parallel, how hard that work is. Ed's working to develop the algorithms. Ed's working to map the cilia. Ed's working to create the database of that kind of information. But he also needs the algorithms to reflect this. He needs to correlate that with some kind of signal, and he needs to do it fast. So he's been working on the acceleration of the signal processing so that he can approach real time, and that means he's had to he's had to work with special linear math kernels. He's had to work with special accelerators, field programmable gate arrays. The programming of the field programmable gate arrays had to be done both for the math kernels as well as for the specialized algorithms for Ed's signals. It's been a very collaborative project, very demanding project, as demanding in the math area and the software area as your electrical and mechanical aspects in dealing with Ed's technology, other aspects of Ed's technology. Okay, Ed, I hope I said something that you wanted to get out there. Let me go on. Okay, so we have a diagram here which gives some manifestation to the technology, some manifestation to the end unit that the technology is going to fit into. Next slide is...
Then we get to the manufacturing design phase. Excuse me. I wanted to make one other point on the previous slide. Is often there's a negotiation that goes on between the user, the technologist, and the product developer, and it is what's the minimum feature set. And so on that previous slide where we had the detector and then the amplifier, and then we have all these processing steps, we would be asking the question, is it possible to get the nonlinear, one aspect or two aspects of the nonlinear processing clear up into the sensor? Is there a sensor available that mimics that close enough? Just one or two features. Because anytime that you can take processing software of that magnitude and distribute it throughout your system, you end up getting way ahead later on. And I wanted to just use this one analogy. A good friend of mine was developing a product. He was the technologist. He got into the product development cycle, and he was getting to the point where he needed to minimize the parts, and he was tired one night in the lab, and he said, okay, here, it's not working. And then he had a lens, and he had several other systems, and he accidentally took out all the lenses. And then he went and got some coffee, and he came back, and it worked. And so he sold it, and he reduced his part count by 50%, and he reduced his bill of materials and the cost of it significantly. And he was sharing that with me one day, and I remember thinking, the best part really is no part. And that's because he was able to make good money off that product, but he had to think outside the box. So the key elements here, the design process and the build production fixtures for volumes, don't overbuild, the design workflow areas for maximum efficiency. It all gets down to how much it's going to cost to get this product produced, and determine the minimum number of parts required for final production. Then the key principle is keep upfront production expenses minimized until the sales take off. Be a sales-driven organization. Floor space is inexpensive, especially right now. Personnel is not. It's the only thing that costs any money right now is personnel. And the best part is no part. If you keep that focus clear through your whole design, and you continue to minimize parts, you'll have a product and you'll have a business that people will come to and they'll enjoy, and you'll enjoy building it as the years go by. I want to thank you for listening.
This is Bernie. I'll wrap this up quickly because we are at 11 o'clock, and boy, we stayed on time. Congratulations to all of us. In wrapping this up, I'll pull things together by reminding everyone that we started out wanting to explain that the development cycle is a continuum. We've worked to show that by taking ourselves and you through the three development phases of technology development, engineering design, and manufacturing design, so that the technology has now eventually evolved through these phases into an end-use product. Though we've laid out lists of specific steps, we touched upon those that we think are more important, at least more important for speaking to in a webinar like this. We want to thank Ed Large and Mike Stauffer for permitting us to use their technology as an illustration. And it's a technology that a number of us think is just so interesting, so exciting, and we encourage you to continue to advance that technology. The next webinar will be in, I believe it's a couple of months. It'll be in June. The topic for the next, did I say technology? I meant webinar. The next webinar will be entitled Translating Technology into Business Terms. This is where we will start to dissect the technology and understanding it, start to translate it into some of these design issues, start to translate it into marketing issues, start to identify what the opportunity is for a third party to get involved or for an investor to get involved, and in general, help to pull the technology forward into the marketplace, but to do it in a way that we're really not pushing it out there. We're pulling it towards an end user who has a need for the solution that your technology is bringing in. I want to thank all of you for being at this webinar on behalf of Chester Straub, our Executive Director here at TRDA, and the TRDA staff, and myself. Thank you for participating. And Don?
Yeah, I'd like to thank everybody for joining us here today, and I think that you could see that we really enjoyed the subject matter and our interaction here, and hopefully it came across to you guys, and we're really interested in any questions that you have either now or in the future. Maybe as you ponder what we've talked about today, feel free to contact us later with any questions that maybe you come up with at a later time.
Yeah, this is Reader Ward, and I certainly appreciate you tuning in today. I also want to ask forgiveness to Circular Logic for stepping on their technology. But I enjoyed learning about it to see how it might solve different problems. Thank you.
Thank you all. We will open this to questions and answers. The way you'll communicate with us is in the lower right-hand corner. Write your text questions, and we'll respond to them, and we'll hang around as long as you'd like for us.
There was one higher than that.
we're getting thank yous. That's very, very kind of you. We, of course, want to answer some questions. So we're scrolling through any questions.
Well, Bernie, I think one question I saw there was the question about how they can get a hold of the presentation itself. Can you talk about what we should offer there?
These slides will be made available to all of the attendees at this webinar. We will provide them electronically. We don't yet know whether we'll personally send them by email or whether we'll have a location with some kind of a code word on the website. But the presentation slides will be made available.
There was also a question of whether this technology could be applied to sonar.
To sonar, sure. You know, absolutely. Any type of, in my opinion, any type of signal processing, especially something that is variable over time in a way that's similar to normal auditory sound, like a sonar, or as we had mentioned previously, radio waves. This technology could be applied to both of those areas, in my opinion.
We're scanning through the questions now again.
If we go dead for too long,
Well,
Bernie's going to start singing.
Ask a question.
We're just getting acquainted with the technology, and the scroll bar seems to have an electronic spring to it, and we're rereading the questions too many times here.
Yeah.
I think, Reader, you know, when you were saying here a minute ago about this idea of the guy that took out all his lenses and got his system to work, then, you know, that's clearly then an area that you want to find out about in the technology development phase, and not get your product out there with 20 lenses in it, that you bought 5,000 of these lenses, that you then realize, well, if I don't use those lenses, I have a better product.
That's right. And I remember, to elaborate a little bit more, I remember he had a laser, he had a diffracting device, and he had all these lenses in between, and a detector. And in the end, he needed a laser, he needed a diffracting device, and he needed a detector, and that was it. Mm. And he was able to
probably cut down on his attenuation that way. Then
it did. The performance went way up, and users loved his product when they bought it.
Gentlemen, one of the questions we just received was a request to put the contact information up here again, so I'm doing just that.
And this is Reader. One of the focus of both Don as well as my companies is working with entrepreneurs and startups. We appreciate all the work that they've gotten done by the time they walk through our door, and so we understand, having done this very similar things ourselves, that it's difficult to get to the point to where you're willing to share the technology. And I'm sure Don would say
yes. This is Don. I agree totally with that. And you know, one thing that I think we both can offer the entrepreneur is the ability to be honest with them and tell them, you know, is this really a product that's viable? Do we feel then that, you know, looking at how you're approaching the problem, do you have all the capabilities to get it to the point where it is a real product? And that could be resources as well as the technical capabilities themselves. And we try to assist them in whatever ways we can to match up the abilities of the entrepreneur with really what they want to accomplish.
Yeah, that's a good point. The honesty portion of this is Reader again. What we try to focus on is never just to take a job for the job's sake. Make sure that there's a product that's going to come out of it, which will lead to other products and sister and brother products, which people can make money off of.
That is okay. Gentlemen, one of the questions that just came in from a member of the audience group is this. They want to know if the same technology development process applies for products.
The products.
Okay, for products that cannot be manufactured by the startups, but instead needs to be licensed to large companies such as Siemens or GE. To be precise, he's referring to wind turbines.
Well, from the technology development phase itself, it's really the same, because you've got to identify the feasibility of your product, and you've got to identify these differentiating features. And to be able to have something that could be then licensed to a large company, you need to go through that whole process yourself and document it. I think Rita will address probably the product and manufacturing areas. Now, if you're looking at licensing technology, then you do have a few different types of considerations there.
That's correct. And, I agree with Don, is that if you go through the whole process, then you'll know better what to license. What we've seen many entrepreneurs try to do is license too early. And when they license too early, they'll go show their technology to a larger company, and the larger company will just develop it themselves, or a flavor of it that can't really be prosecuted later. So we've been through a few licensing deals, and the ones that have worked the best is when they've gone through the whole product development process, they have a working prototype. That's when, and they have, of course, patents and whatnot to protect them. That's when a licensing deal is much easier to set up with a company.
Yes, this is Don again. Especially from the point of view of the technology itself. If you try to get into a deal too quickly, then maybe you haven't really developed all of the technology, and maybe you only have a small aspect of all of the technology you could have developed, and that would make then a large company, it would make it easier for them to just sidestep you and develop the rest of the technology on their own, and so you're not really working from an advantageous point of view there.
This is Bernie. It's very important for us to put in here the legal aspect of this, and that any discussion with a third party about proprietary information or proprietary design needs to be covered wisely by a non-disclosure agreement or a confidentiality agreement, same thing. I've over the years had the practice of narrowing what would be discussed, because if the discussion area is too broad, too much information is presented, and then you are confined to never being able to work on that proprietary information shared with you, and you are preempted from further work. So the confidentiality agreement or secrecy agreement is very important. It's not casual. There should be some legal guidance that is sought to make sure that it's done right. But to be done right, the attorney who does it with you needs to have some kind of technical background, which is the reason why patent attorneys have to be scientists or engineers ahead of time. Michael Stauffer from Circular Engineering has provided part of the answer to the question, Don, that you had answered about radio frequency waves. Michael said that, yes, their technology works on sonar and radar too. Could any particular time-varying signal, they haven't looked in depth beyond these because they have a particular focus right now, but any time-varying signal might make their technology pertinent.
Great.
We're going to check through here to see if there are any questions we missed.
I think I see a question here about the time process. The time it takes to go through this whole process.
Oh, I thought they were talking about, it's interesting, Don, because I thought they were talking about the webinar time.
My interpretation here, I think, is that they're more interested in getting their technology out into the marketplace.
I'd say that's a very important question, Don. Why don't you take a shot at that, even though the answer varies. Let's give them a bit of
certainly the
some
answer
guidance.
Will definitely vary, but I think that it's very important that you spend enough time in each phase here to get a good product, because there's an old saying that to end well you need to start well. And so I think from the point of view of developing the technology, if you think about a typical SBIR funding cycle. Really, the technology development maybe is the phase 2 area here, and so that typically then maybe the SBIR program will give you about 2 years to get through that. So I would say that within 2 years you should be able to have a product that can start getting out there and making money. Of course, the problem that you have is, do you have the resources and the funding to get through to that point? So it's critical to understand the resources ahead of time and not to get into the technology development of a product if you do not have those resources to see it through to completion. Reader, what's your estimation on that?
I think that's a very good rule of thumb, because we developed a product internally that was multidisciplined, and we developed it 3 years ago, and we're expecting our first order next month. And it's not that we thought it would be 2 years ago, but it's other factors come in. You have everything done, you're ready to go, and the economy goes down. You have everything ready and your requirements change, and the requirements have changed on this probably no more than 20 times. And that's not an exaggeration. So what I encourage people to do is be in it for the long term, conserve your cash up front, but do a thorough job, as Don said.
I think we understand, though, of course, that an entrepreneur group is going to be cash limited, and they're going to be looking for ways to generate income. And so this is always a critical aspect of the small business and the entrepreneur. How do you keep your head above water until you get to the point where you have a product that can get out there and make money?
And some of these answers include a business perspective and business involvement. And over the future webinars, we'll touch on parts of that answer. I think we ought to call it quits. If there are any last questions, please send them in now. We'll address them. Otherwise, we'll say that we're done for the day in the webinar, and provide you with a second follow-up. Thank you.
Yes. Yeah, thank you for spending your valuable time with us this morning.
Yes, we very much appreciate it, and please feel free to contact us with additional questions.
Thank you on the part of TRDA for the opportunity to develop and present this webinar, and we'll look forward to the future webinars and those of you who will repeat with us. Thank you all. And Don, Reader, thank you.
Thank you, guys.
Thank you.